So cosmology is the area that I'm really fascinated about because it's an area that connects deep philosophical questions with hard data. And the philosophical questions, they concern the origin of the universe. And that also means the origin of space and time. If you would have asked me 3 years ago how I would judge the chance of inflation being part of the story, I would have said, well, more than 50%, but it's worthwhile exploring alternatives because a theory grows by being challenged with alternatives.
Any sufficiently advanced technology is indistinguishable from magic.
All right, so we'll get started right now with my good friend, my mentor from way back when, one of my thesis committee members, one of my favorite members, the second one to appear on the podcast, Professor Robert Brandenberger, second only to Peter Timby, who was my actual thesis advisor, who did appear on the podcast many years ago on Father's Day, because as you know, Robert, there's sort of a fatherly, motherly connection between a student and their mentor. And I certainly feel that way about you, although you're not old enough to be my father, but sort of like a cool, rich uncle. Anyway, Robert, how are you today?
I'm quite well.
It's great.
Sabbatical year.
Oh, that's great. And you're in McGill now? You're in Montreal?
Yeah, I'm in Canada, but on Sunday I'm heading back to Europe.
Oh,
to
nice.
Switzerland.
Very nice.
I'm originally from Switzerland, so it's
right.
like going home.
That's right. That's right.
So I can spend some time at the beach or walking the mountains and thinking about things.
Yes, and I remember you walking around the corridors of Barris and Hawley. You were an inspiration to me and many time past guests, Stefan Alexander. I just had the pleasure of spending some time doing some thought calculations with Stefan this past weekend for Mother's Day. He visited here. And so, Robert, we've connected again because of a very, very interesting scenario, which was that on the website Reddit, which has a lot of crazy stuff, but some interesting stuff about physics, there was a paper about your work. One of your papers was the trending topic, and that means it was the most viewed, most talked about topic in all of physics. And I thought that was pretty much a sign that I was overdue to have you on the podcast. I've actually had a note in my calendar. I checked it from November 2020. So I beg your forbearance and forgiveness for not having you on sooner. But we're not going to talk about that paper, which is about converting gravity to light, or maybe the other way around. But we're going to talk about very, very interesting topics. And that has to do with perhaps alternatives to the standard paradigm. And I remember you as a mentor that you taught me many things. And one of them was to not be afraid and to take risks, but take prudent risks and pursue avenues, even when people didn't really think they would bear fruit. I've had a lot of people on this podcast who are very negative about string theory, a lot of people that are negative about inflation, but I've also had more people that are positive about those things, including your collaborator, Kamran Vafa, who I had on many years ago as well. And so I want to ask you, what is the most fascinating area of physics that you're currently researching right now?
So as you know, I work on a wide range of topics, all theoretical cosmology. So I'm a little bit handicapped because I don't do computer work. So I have to do work with pencil, paper, and most importantly, an eraser, because often the ideas don't pan out or I make calculation mistakes. But so cosmology is the area that I'm really fascinated about because it's an area that connects deep philosophical questions with hard data. And your group is one of the groups providing the hard data. And the philosophical questions, they concern the origin of the universe. And that also means the origin of space and time. Mm-hmm. Now, so you mentioned two things. You mentioned string theory and inflation. So let me focus first on inflation. So over the past 30 years, inflation has become the paradigm of early universe cosmology. In fact, it's made it into astronomy textbooks. Mm-hmm. You read an astronomy textbook, and the section on cosmology starts with saying that the universe began with a big bang and then followed a period of inflation, which is exponentially growing space, like exponentially growing prices. So now there's a sort of a problem with this scenario. And if you would have asked me 3 years ago how I would judge the chance of inflation being part of the story, I would have said, well, more than 50%, but it's worthwhile exploring alternatives because a theory grows by being challenged with alternatives. And if you work out good alternatives, and then you can basically challenge people who work on the standard paradigm to do better. But so my view has changed, and my view has changed because of something which we call the TransPlankian censorship conjecture. So the TCC, and this is a paper which Bedroya and Waffa wrote now almost 4 years ago, 2019. There was a follow-up paper which I co-authored with them and with Mariana Loverde. So inflation is the idea that space expands exponentially. And that means that if we have little waves on this space, then the wavelength of these little waves also expands exponentially. So in our models of inflation, if we look at the wavelengths of small density perturbations, the density perturbations that your experiments are measuring, if we trace them back to the early universe, then in the standard inflationary models, we find that they emerge with a wavelength which is smaller than the Planck length. And maybe not all of your listeners know what the Planck length is, but it is the boundary of our knowledge. We know that on length scales smaller than the Planck length, we don't understand the physics. So the problem for inflation is that everything that we measure today, according to an inflationary scenario, starts out in this window where we don't understand the physics. And so based on this argument, Waffa and Bedroya postulated that there's a new fundamental principle of physics that says that this situation never should happen. Little density perturbations on length scales smaller than a Planck length should never be able to become larger than a particular length scale, which is called the Hubble radius, which is the inverse expansion rate. And this is sort of the length scale above which these little waves, if they start from quantum mechanics, they kind of become classical. And we all measure classical things, distribution of galaxies, microwave anisotropies. So this TransPlankian censorship conjecture says that things that are now classical never come from this TransPlankian region.
Is this related to like a cosmic censorship or a
yes.
Okay. Go
yes.
on.
And so after this initial work, I was asking the question, where does this come from? How can we actually argue for this? And I know that Roger Penrose is a frequent guest on your program.
That's right.
And I guess you were referring to his censorship conjecture. And so the first justification that I give for the TransPlankian censorship conjecture is an analogy with Penrose's conjecture. So what Penrose says is the following. Penrose notices that black holes with small charge, they have singularities in their center, but an observer who's outside of a black hole never measures anything that comes from this singular region. So the observer is protected by a horizon. Now, Einstein gravity allows for solutions where the charge is bigger than the mass. And for such black holes with charge greater than the mass, the poor observer far away from the black hole is not protected from the singularity. And so Penrose postulated that in the theory that completes general relativity, such pathological solutions cannot arise. So now if we translate Penrose to cosmology with a very well-defined translation schema, then we get precisely the TransPlankian censorship conjecture. Now, there are two other justifications that I can give for the TransPlankian censorship conjecture. And they're both associated with words which are quite popular these days in the high-energy physics literature. One of them is unitarity, and the other one is entanglement entropy. So let me talk about unitarity first. So we would like to have a theory in which we can calculate how things evolve from the past to the future in a well-defined calculation way. A theory which satisfies that is a unitary theory. So the word unitary also comes from doing it at the quantum level. Now, you can show that in a model, in an expanding universe, if we describe things using what's called effective field theory, which is Einstein's classical theory coupled to what physicists learn in graduate school. You take gravitational waves, you take matter fields, you expand them in Fourier modes, meaning plane waves. You take each plane wave separately, and you view each plane wave as a harmonic oscillator. So that's effective field theory.
Yeah.
If we try to do that in an expanded universe, then we have to continuously create new plane waves. That's non-unitary. And if we want to protect classical observables from this problem, then we're going to get the TransPlankian censorship conjecture. And the third justification is if we want the entanglement, if we want the entropy density at the end of inflation to be smaller than the entropy density that we need at the beginning of the standard Big Bang phase of cosmology, then inflation cannot last too long. That again gives a TransPlankian censorship conjecture. And so based on this TransPlankian censorship conjecture, based on these unitarity and entropy considerations, I will make the provocative claim that the models of inflation that we have violate unitarity and violate the second law of thermodynamics.
Can I pause you for 1 second, Robert? Because I'm sure people are asking, when I hear unitarity, I think back to my quantum mechanics class with Leon Cooper or Frank Levin, your former colleagues when you were at Brown. And I think back to interpretations of quantum mechanics. I think back to the Copenhagen interpretation. I think back to things that respectable physicists should not enter into until much later in their career. Are these unitarity considerations, are they in any way related to an interpretation, or do they have a direct physical, falsifiable, observationally motivated a place in terms of their non-interpretive behavior? In other words, is it just a matter of interpretation and then we should shut up and calculate, as David Merman used to say, or are they real manifestations we can get access to physically?
I claim that there are real manifestations that we can get access to. They have no relation with these measurement issues of quantum mechanics, the ones that you alluded to. So now one way I can make this specific is, so I said that if you want to treat inflation the way you usually treat it, you have to continuously create new waves.
Yes.
Waves of different wavelengths. Now, you've given me a recipe for setting the initial amplitude of these waves, if you create them. And this choice is going to affect observations. So I can give the standard choice, which is not well justified. But if I give a modified choice, then I will get completely different results, for example, for the spectrum of microwave anisotropies, which you measure.
So different from the Harrison-Zeldovich.
Different from the Harrison-Zeldovich. And different not only in minor ways, but in major ways.
Interesting.
So it's based on these problems that I changed my mind. I actually think that alternatives to inflation probably are more promising at the present state.
Really? So when I've talked with my friend Paul Steinhardt or Neil Turok and many others, Anna Aegis, who's a brilliant young cosmologist in New York and also in Germany, And I tell them the following kind of complaint from an experimentalist point of view. I love alternatives, but better than an alternative would be a theory that doesn't invoke some of the aspects of inflation. In other words, it should be as radically different from inflation in my humble experimentalist perspective. In other words, it shouldn't have a multiverse. It should not have different runaway chaotic behaviors. It should not have even a scalar field. And yet, correct me if I'm wrong, all of these, including Sir Roger's conformal cyclic cosmology, which I've talked to him about specifically, and Aegis and Neil Turok and Paul Steinhardt, I've said, you all have the same feature that our good old friend Sir Fred Hoyle and my late colleague Jeffrey Burbidge and Margaret Burbidge had, which was a creation field. They called it the C field in quasi-steady state cosmology. Nowadays, Paul and Anna, they call it just a scalar field. Andre Linde, past guest, calls it the inflaton field. And Sir Roger Penrose calls Erebons and other phenomena. They're objects that we don't encounter other than the Higgs boson. And so I say to my theorist friends, can you give me a model that doesn't have a scalar field? Because at some level, you have to still posit, where did that darn scalar field come from in the first place?
That's right. So I completely agree with what you said in everything.
Mm-hmm.
To even amplify on what you said, with scalar fields, you can get any cosmology you want. And so now, my friend Slava Mukhanov, who's one of did this foundational work on inflation, how inflation gives rise to a mechanism of forming structure, he would agree with the following statement that I make. If the simplest scalar field model does not give something interesting, so if in your theoretical model you have to tweak the scalar field, then it is no longer a good model. But now you asked another question. So are there models of early universe cosmology which do not involve scalar fields?
Yes.
And the answer is yes. And so I've been working I proposed, together with your guest, Kuhn-Waffer, a model of early universe cosmology based on superstring theory called string gas cosmology. This was back in 1989. And we have an improved version of that recently called matrix cosmology. So the answer to your question is yes. I'm very keen on working on cosmological models which do not involve a scalar field. And I'm going to make a prediction for your observations.
Okay. And
that prediction is going to be a consistency relation between the tilt of the B-mode polarization that you're going to measure, the gravitational wave spectrum, and the tilt of the density perturbations. It's a specific relation. And for people who know the nomenclature, it's NT equals 1 minus NS. And this comes from a model based on superstring theory. Now, can I make a side comment?
Of course.
Okay. Now, I'm critical to about inflation, as you gathered, but I'm actually I like string theory. I think string theory is a good starting point to try to understand the universe. And I know that this, among many people, is an unpopular opinion. Anyway, so in our models of our universe cosmology, indeed, we start with superstring theory. However, we have to start not with a toy model, not with an effective field theory based on superstring theory, but with something truly stringy. And so in our old work with Kuhn-Waffer, we sort of said, well, what's the difference between a theory based on strings and a theory based on point particles? Well, all of your listeners can see the difference. If you have a string, you can stretch it and you can tweak it. A string can vibrate. And if you have a string on a donut,
Mhm.
the string can wrap the donut. Point particles can move on the donut, but they cannot wrap the donut. And there are also no vibrational modes of a point particle. So Kumanwatha and myself, we were asking the question, if you start with the same idea of a background space-time that we usually use in cosmology, and instead of having point particles on this space-time, but instead we have strings, the basic entities being strings, will we get a difference? And we realize that there's a big difference. And to illustrate this difference is the following. I can say the following. You take a box of strings and you compress it. You take a box of point particles and you compress it. Now, if you take the box of point particles and you compress it to smaller and smaller and smaller sizes, the temperature becomes higher and higher and higher without a limit. And eventually the temperature reaches infinity.
Yes.
But you take a box of strings, you compress it. Initially, the temperature rises, but then the temperature approaches a limiting value and the increase in temperature slows down. Instead of
a singularity.
There's no more singularity. You start producing the oscillatory modes of strings. And if the box becomes small enough, then all of the energy goes into strings that wind the box, whose energy becomes small, and the temperature goes down to zero.
And that's this Higgs-Boson. Maybe
that's this phase in which the temperature is close to this maximal temperature. This is the phase that we call the Hagedorn phase.
Hagedorn phase.
It's named after Hagedorn, who first worked out the statistical mechanics of closed strings.
So these
in the late 1960s.
These strings are sort of behaving like degenerate matter, or they have a and that's not to say there's anything wrong with that, but they have a different equation of state than a shoestring or a particle of dust or even dark energy, if I'm understanding it correctly, because they must behave in a degenerate fashion such that you cool once you exceed in the approaching from high to low temperatures, because then they cool down again. The network, the string network, which is also another phenomenon. So if I'm wrong, correct me. But point particles, as you said, you can interact point particles, but they don't entangle. But if I'm not mistaken, the strings can actually interact. They can entangle. They can do more than they can also scatter, but that's not all they can do. Correct?
That's correct.
Okay.
But then you go back to this equation of state, which you mentioned. So equation of state. So if you just have clumps of matter, cold matter, that has zero pressure. If you have the radiation, the microwave background radiation has positive pressure. Now, if you have a gas of strings, what happens is that depending on the density of the strings, this equation of state changes. It starts out at like radiation, and then becomes something like cold matter, and eventually becomes something which has negative pressure. Not as negative.
Wow. So it actually goes from this is for my cosmology students that are studying this right now. It goes from an equation of state of 1/3 to an equation of state of zero, W equals 0, to an equation of state of less than minus 1/3. Correct?
That's right. It goes back. It goes to minus 1/3.
Okay.
Now, again, in your cosmology class, you'll be studying equations based on Einstein's theory.
That's right.
And then, if you just couple strings to that, you will still, even when the box is small, the Einstein equations will say it will still expand.
That's right.
So you take your box of strings, and although the temperature is decreasing again, the box will still decrease. So now there's a second aspect of strings, namely what that makes strings different from point particles is the following. What do you actually mean by position? So how do you measure position? So in usual physics, you take particles and you see where they land. You shoot particles, you look at their momentum, and they land somewhere. They scatter off a point, and that's how you can determine position. But now for strings, you actually have these windings.
Right.
And there's actually a second way of defining position. So if you have a gas of strings, you actually have two ways of defining position. There's like a position and a dual position. And if the box becomes small, if it becomes smaller than the string scale, then any experimentalist will be using the dual description of defining space. And in terms of that, space will be growing. And you will have a bouncing cosmology with no singularity.
So you'll start off, and what will be the spatial geometry in the three different phases?
This is now the point. So the Achilles heel of our early work, 1989, is that we just postulated that we would always set space was going to be a torus, either small torus or large torus. So a 9-dimensional donut. Because in string theory, you have 9 dimensions of space. Now you can ask me why this is not a problem. This is actually a very nice feature.
Really?
It's a very nice feature, yes.
Why is that?
Okay, so this is now a digression. And again, so the way that I will answer it, I will give you a defense of string theory against some of the popular criticisms. And one popular criticism is that with string theory, you can get anything you want. You have this landscape of possibilities. So I'm sure many of you guys.
I've actually said that. I have to confess to you, as my father, in a certain sense, Robert, that I have used that complaint. I have used that attack against none other than one of the people who founded string field theory, and that's Michio Kaku, who came on for his book last year, The God Equation, in which he claimed, I said to him, well, you know, Michio, I don't have to, he said, well, string theory is often accused of predicting anything, as you just alluded to, but that's just like saying in Maxwell's equations, you have to tell me what the ground state is. I said, but Michio, once I tell you the ground state, everything's determined. And furthermore, from just the field strength Maxwell tensor, I can get all the equations of all the behavior of every dynamical object in space-time, at least in that simplified version. Whereas you need to specify it for each one of these models. And furthermore, it could change as the landscape and the swampland conjecture sort of highlight. So anyway, I'm just confessing to you, Robert, that I have used that attack. And but the first person, the only person so far, maybe you'll be the second person, but the only person to say that string theory makes a prediction that's experimentally verifiable is your colleague, Cumran. But it wasn't all that satisfying, because he basically said that string theory predicts the mass of the electron can vary from 10 to the 16th Planck masses to 10 to the minus 2 Planck masses. So in other words, there's a lower limit and upper limit, but you're not predicting it with precision that any high school chemistry student would be satisfied with. Anyway, sorry for the digression on top of the digression, but you're right. People do criticize string theory for the infinitude of possible ground states, essentially.
But now let's go back and forget and throw out the strings and go back to point particles. If we do that, we can have any number of dimensions of space and time. No one tells us why there should be 3 dimensions of space.
Yes.
4, 5, 6, 7, 8, 9. We can have arbitrary number of fields. We can have 1 electromagnetic field, 2 electromagnetic fields, 3 electromagnetic fields. We can have 1 scalar field, 2 scalar fields, 3 scalar fields. We can have any kind of potential we want for any of these scalar fields, and these fields can have any range. So it's a huge swampland of theories if we forget about strings. Now comes string theory, and string theory says that string theory is only consistent in 9 plus 1 dimensions of space and time. So 9 dimensions of space and 1 dimension of time. So it's restrictive. Now, I haven't worked out the detailed connections between string theory and particle physics models. So I can't tell you at low energy how many particles string theory predicts. but someone who has good mathematical talents will eventually be able to tell that. So all scalar fields that emerge from string theory have a geometrical origin. Their potentials are constrained. So among all possible effective field theories that you can get from point particles, this huge swampland, there are only small islands that stick out, habitable islands. Unfortunately, it's not just one island, it's a number of islands, and it's a landscape. So you see, this is why I argue that the criticism that string theory predicts anything you want is misplaced.
Mm-hmm.
It is not as predictive as we would like it to be. Maybe eventually it will be, but it is a step forward.
Mm-hmm. Interesting. So
and then I made a prediction for cosmology, a specific prediction, which is the one I just told you.
Right. So if we pivot back to this notion of the predecessor, let me explain it like this. Maybe they're prerequisites of these various frameworks for the early universe. There's Sir Roger Penrose conformal cyclic cosmology, which requires these error bonds and this strange form of matter, as he calls it, that evolves and changes. And then it also emerges from a phase of black hole entropy with conformal dynamics that I still don't fully understand. But be that as it may, it involves a scalar field. Let's just say it like that, or it involves a new physical manifestation of field. Next, there is the creation field, the C field of quasi-steady state cosmology. There is the scalar field of the bouncing cosmological model of Paul Steinhardt. There are alternatives as well that have scalar field, and of course the inflaton scalar field. Now, I always point out there's only one scalar field that we know for sure exists, and that's the Higgs boson. But that's a very different type of field than what the inflaton would be. So I guess the problem that I have with that is, who put that there? Where did it come from? And so I would ask you the same thing. Is the minimum prerequisite for string gas cosmology just the existence of space-time? I mean, all these other fields have space-time, plus they have a scalar field. So it would be an Occam's like simplification to only require space-time. Am I getting that right?
That's right. Absolutely right. So our input was space-time and a gas of strings.
Mm-hmm.
But now, you see, there was a problem with this scenario, because we don't just want to postulate a space-time that behaves in some arbitrary way.
Yes.
We want to derive how it evolves in this early phase. And in this early work of 1989, we had put it in by hand.
Mm-hmm.
So in my opinion, that was the Achilles heel of our early work. Mm-hmm. And so in our recent work, we've been trying to improve on this.
Mm.
So, now, I completely share your view that we should not try to invent new scalar fields. So we're going to try to do something different. Now, at the beginning, I was sort of arguing that if we want to describe the early universe using fields, then we are faced with this problem, potential unitarity problem.
Yes.
So we shouldn't just be using fields. We should be really using something fundamentally new. We should be using what physicists in my field call a non-perturbative definition of string theory. So let's step back and analyze what I mean by that. If you go back to particles, then classically we know what particles do. Like on a billiard table, we know how particles move. Mm-hmm. Particles scatter classically. We can include quantum effects in the scattering of particles. These are the things that you do in accelerate experiments. But if we want to describe the theory of particles, the theory of an arbitrary number of particles, we have to replace the notion of a particle by a field, like the electromagnetic field.
Yes.
And a particle will just be a little localized excitation of the field. Now, in string theory, we know how strings evolve classically. And after a lot of work, we've also been able to study the quantum mechanical scattering of strings. But we don't have a theory of an arbitrary number of strings, the analog of the field theory of particles. But there is a proposal. And the proposal was made in 1996, 1997 by Banks, Fischler, Schenker, and Susskind. It is a matrix model. And this was our starting point. So now you see, some people who you've interviewed are radical. They want to do things that are completely new. I'm actually, even though I'm not perceived as a radical, I'm actually fairly conservative. I just said, well, we need a non-perturbative definition of superstring theory. What is the best thing on the market? And so we took that. So do you want me to say a few words about that?
Yeah, absolutely. And I want to make sure we have time to go over some of your slides at least too.
Okay, good. So we are starting with a theory in which the basic ingredients are matrices. And there is no space. It is a quantum mechanical model, like a system of spins, but here it's a set of matrices. So it's a quantum mechanically well-defined system, the very large matrices, n by n matrices where you let n go to infinity. But there are no singularities. It's a well-defined matrix model. There's time. And what we do is we consider this matrix model in a high temperature state. Now there's no more evolution. There's no more space, no more time, no evolution. And our goal was to try to see what we can get out of this well-defined starting point. So in our recent work, we've been able to get a construction of emergent time, emergent space, an emergent metric. So a metric is something that describes a distance in space, and an early universe cosmology out of that, including things that you can measure in observations. Now, the time that emerges out of this construction, in the limit where you take the size of the matrices to infinity, this time is continuous, not just discrete ticks of time, but it is a continuous interval, like a string. And it ranges from minus infinity to plus infinity. So there's no Big Bang singularity. The space that emerges, that we had to work a little bit harder, also is continuous, and it is also infinite. So the space that emerges is infinite, but it is infinite only in 3 dimensions, not in 9 dimensions. So even though the theory is a theory of 9-dimensional space and 1 dimension of time, what emerges is only a 3-dimensional infinite space. And the other 6 dimensions are some structure which has not even a well-defined geometrical meaning. Okay, then we have it. Now that we have space, we can give a definition of length. And once we have a definition of length, we have coordinates. We know what the metric is. And what emerges is that this metric is spatially flat. So we don't get, the space that emerges is not like the surface of a sphere or the surface of a saddle, but it is just flat. It is something that evolves in time, but the space is flat. Okay, so we don't need inflation to produce an infinite universe. We don't need inflation to produce something that's flat. The problems which inflation was initially designed to cure are automatically cured in this approach. And there are no scales in this approach.
So there'd be no deviation from the Harrison-Zeldovich.
Now come the fluctuations. Since we have a thermal state, we have thermal fluctuations. So we can compute the perturbations, and we find that we get something that is roughly consistent with observations. We get to first order in the approximation, we get what you just called the Harrison-Zellweger spectrum, something that's scale invariant. So if you take a box and you look at fluctuations in a fixed box, then independent of spatial scale, you get the same magnitude of fluctuations. That's scale invariant. So the first approximation, we get that. And if we now go back to our string gas cosmology toy model, then we automatically get the tilt, get the deviation, and we get this consistency relation, which I gave you. We also get gravitational waves. And there's no cosmological constant. So this is something that I'm really excited about. And obviously, this is a beginning of a research program. But I think I've answered your program. This is an attempt to obtain an early universe cosmology which does not involve scalar fields. Indeed, I share your criticism against these various other approaches which involve scalar fields. I think they're very interesting. In fact, I think if you like bouncing cosmologies, I think you have to pay close attention to this ekpyrotic scenario, which was initially proposed by Curie, Ovold, Steinhardt, and Turok. Yes. Because among bouncing models, that's the most promising, in my opinion.
Yes, and that's one of my that was one of my questions from our friend Stefan Alexander, your former graduate student who's gone on to become a professor at our very own my very own alma mater. Right. Also had some questions from my colleague Amit Yadav, who is working as a scientist for me for many years. And maybe while I'm getting those up, then we could get the slides that you have. We've actually covered a lot of the slides, but I want to get this slide. If you could put up your slide 17, because this is a terrifying slide to me. This is terrifying to me. You did mention there are gravitational waves. You did mention there'd be a consistency relationship between the gravitational wave power spectrum, the tilt of what's called the tensor power spectrum for the aficionados out there, N sub T, and the relationship between N sub T and N sub S.
Maybe you should hold off because I think you are too scared of this slide.
Okay, so go on. You take it away, Robert.
You see, this slide is in the context of inflation. Mm-hmm. It is saying that if you try to construct an inflationary model, which is consistent with the TransPlankian censorship conjecture, then you need low-scale inflation, and then you get these negligible primordial gravitational waves.
Yes.
Now, you see, I think that this is not the way to go because of all these problems. You should not be scared about that. But if you hear people say that that a large R is a smoking gun of inflation, that's where you should object. A large R is not at all the smoking gun signal of inflation. Alternatives to inflation typically produce a fairly large R.
Well, not the alternatives of conformal cyclic cosmology or
maybe not that one. That one I haven't studied, but in our realization of Paul Steiner's ekpyrotic scenario, we get a fairly large value of R, and in string gas cosmology as well. And we get a rough consistency relation, which I can tell you privately, which gives us a magnitude of R, but it's only rough, so I prefer not to mention that. But maybe you see. Since this is bad news for standard models of inflation, let me go to another slide, and namely the criteria. So if you're an inventive young person, for example, a young listener to this show, and you want to construct your own model of the early universe, then what I'm going to give you is the criteria which you have to satisfy. So first of all, this is the data that you need to reproduce. So here, the horizontal axis is angular scale, large angular scales, small angular scales on the right. And the vertical axis is amount of structure, amount of anisotropies. And the black dots are the data. And it is the data that you have to fit. And this is actually old data. Now the error bars are smaller. And there's a red theory curve, which is not important in this context. Now, the red theory curve was actually predicted 10 years before inflation by Zeldovich and Zunyaev. and people send you. And this is a graph which I took from the Zeldovich-Sunyaev paper of 1970. So here, the horizontal axis is space, and the coordinates that I'm using are coordinates which are expanding as space is expanding. And the vertical axis is time, and this time here is the time when the microwave background is released. Now, Zeldovich and Sunyaev assumed that there's some unknown mechanism that produces waves of density waves at very early times on all wavelengths with a scaling invariant spectrum. Now, it is a fact that these waves are frozen in. They are standing waves until the wavelength becomes equal to this length, this diagonal curve, which is actually the standard Big Bang horizon. And then they start to oscillate. Mm-hmm. So the wave that you catch here, that crosses the horizon at recombination, you catch it as a standing wave with maximal amplitude. But this wave, which has done 5/4 of an oscillation, you catch it at a minimum. Mm-hmm. So it is this evolution of density waves which explains these features. So the physics that gives rise to this was well understood 10 years before inflation, but you do need a mechanism that produces these initial waves. And so these are the three criteria for successful early universe cosmology. First of all, the horizon, which is a distance that light can travel from the beginning, has to be much larger than what we think it is in standard Big Bang cosmology, because we have to produce a roughly isotropic universe. And then you have to have a mechanism that generates fluctuations. And in order for this mechanism to be described by causal physics obeying Einstein's laws of special relativity, then the length scale that you produce the fluctuations on has to be smaller than the Hubble radius at some early time. This is the second criterion. The third criterion is the scaling invariance. And so inflation satisfies these three criteria. So time, space, physical length. This is a period of inflation when space expands exponentially. The horizon expands exponentially, becomes exponentially larger than the Hubble radius. Wavelengths of fluctuations grow exponentially. And so if we trace back the waves that you are measuring, Brian, you trace them back, they start out inside the Hubble radius. So here you have the two first criteria satisfied. But if you take a bounce in cosmology, so this is bounce point, expanding phase, contracting phase, no inflation. This is what the wavelengths of the scales do. So time runs from minus infinity to plus infinity, just causality over all of space. Fluctuations start out smaller than Hubble radius. You have the possibility of a causal mechanism. Mm-hmm. And in our string gas scenario, we basically have something that looks like quasi-static, and it gives rise to a space-time diagram that looks something like this. But now let me give the challenge to the young people, the young people who want to work in this field, who maybe are not even undergraduates yet. Mm-hmm. You have to come up with something better than the three things which I just briefly showed you, which satisfies these three criteria. And Brian, you don't have to be afraid at all about this previous slide, number 17.
Okay. Good to know. I'll be able to rest easier because I'm actually not afraid of it. Let me take a detour because that's what I love to do with you. So I think that most things in cosmology do not have a natural scale. In other words, as you show many times, inflation could occur. It could have occurred at a very low energy scale. It could have occurred at a very high energy scale. We actually don't know. There's no lower limit on the energy scale of inflation. On the other hand, there is a lower limit on the amount of B-mode polarization. In other words, there is an amount of B-mode polarization that's not necessarily primordial. Yes. And you hinted at it on a slide, but my colleague here, Raphael Flauger, who you know undoubtedly very well, is one of Steven Weinberg's final students. Raphael and David Spergel and others have looked at this, Paul Steinhardt as well. And this is that because of the what are called secondary perturbations, there is a lower limit. And I think my experimental colleagues, you have a lot of affection and appreciation, and you always did, for people like Peter Timby, my advisor, and so forth. And you were always very connected to experiment. But sometimes I think you give experimentalists a little bit too much credit and praise because there is a sense of dishonesty, I believe, that we are attempting to measure certain things with very big projects, some of which I am very intimately involved with, as you know, the Simons Observatory, the Simons Array, BICEP in the past, et cetera. And that is that we're basically assuming the conclusion that inflation took place because there's a preponderance of cosmologists that do support it, and furthermore, it is amenable. It has a certain pleasing nature to it. It even leads to things like the multiverse and other things that some people find pleasurable, others find distasteful, both to cosmology, but even to the scientific method. We'll leave that aside. My point. Yeah.
So in terms of inflation predicting a multiverse, I would argue that this is not the case. My friend Slava Mukhanov would agree with that. And let me maybe quote something from one of the other guests, Sabine Hossenfelder. She said sometimes people take their equations too seriously and don't think about the physics. And I think this argument that inflation predicts a multiverse where you treat inflation just in terms of your scalar field, this is treating your equations in a domain where you can't trust them.
So similarly, yes, I agree. In fact, people talk about things like the Planck length as being some fundamental building block scale of nature. In reality, if that were true, then the Planck mass would also have to have some fundamental significance. But the Planck mass is the mass of an egg of a fly. It's actually a very large mass. Not to say the Planck length is large. Of course, it's very small. But there's nothing fundamental about it. So people take that very seriously. Elon Musk recently said that, that basically the existence of the Planck scale sets an absolute limit on the number of digits of pi, which I found ridiculous. And but he's an amateur physicist. I hope to have him on the podcast at some point. But getting back to my conjecture, if physicists were honest, let me just say, if I was honest, because I'm not going to impugn the reputations of my colleagues and friends, but if I was honest, I would say to Jim Simons or the National Science Foundation, I'd say, look, we actually have no idea what would happen if inflation has an energy scale that's even detectable. But we know for sure that there must be a fluctuation of B mode fluctuations at a scale corresponding to 10 to the minus 6, a tensor to scalar ratio of 10 to the minus 6 from what are called secondary perturbations. You can explain this much better than I can. But Robert, that's also that is interesting to an experimentalist. We love lower limits. So there's a lower limit on the mass of the neutrinos. That provides a very tantalizing target that we can then optimize experiments such as the Simons Observatory and the CMB Stage 4 project. We can optimize those to detect that lower limit as a worst case scenario. But for inflation or the lack thereof, the lower limit comes from these secondary perturbations. Now, if we don't see those secondary perturbations, I claim that would be interesting also, because that would mean there's something wrong with general relativity in
Absolutely.
So I think, but we know that to detect such perturbations is way beyond the reach of maybe 1,000 Simons observatories. In other words, $1 trillion mission would not be sufficient to detect a threshold of 10 to the minus 6 at more than, 0 sigma, essentially. So I claim I'll just say me, because I don't want to impugn any of your friends or my friends, that we're not being honest, because we're pitching this experiment as the definitive way to ratify, justify, detect, or falsify inflation when it really can't do that. And ultimately, we should be saying, let's measure 10 to the minus 6, except we want to do it in our lifetimes. And I think that's a sign of me being greedy. Who's to say that if Penzias and Wilson wanted to measure E-mode polarization with their first instrument in 1965, that would have been impossible too. So there's no guarantee that nature will cooperate on a timescale of your technology. So I guess this is all a way of saying that experimentalists should not be praised too much, because a lot of times we want to get the job done for our careers and for our own intellectual curiosity while we're alive, but it may not be possible. And so for that's sort of my rant about experimentalists and not putting them on too much of a pedestal.
Yes, I agree with this wrong advertisement of the goal of certain experiments. So I completely agree with everything that you said.
Yeah.
But I think you can make very good physics cases exactly for the kind of experiments that you're working on. One of them is you can, if you manage to find a B-mode, a cosmological primordial B-mode background, you should go after the tilt.
Yes. Because
this tilt relation which I gave you is something that string theory first predicted. And so if you find such a tilt, that would be great news. But there are also much more modest things that you can do. And maybe I can now turn to some of the other work that I don't only work on early universe cosmology.
Yes.
I have several pet topics, but one pet topic are cosmic strings.
Yes.
And
you actually tasked me with a project to do that when I was considering in a crisis state, which I think all graduate students must go through at one point or another, where we totally question what we're doing, Robert. And I'll get your advice to young people at the very end of the podcast. But I had a crisis of confidence. I wasn't sure I really wanted to be an experimentalist. Mark Kamiankowski recently called me a closet theorist anyway. But I did a project with you and you assigned me cosmic strings. And it was about the deficit angle that they would induce and what type of polarization. And I never came even close to solving it. And I apologize, mea culpa. Later on, we moved to Wisconsin. But tell me about these cosmic strings. Why are they so mercurially? Why are you so interested in it? This is 30 years I've known you. Why do they still fixate you so delightfully so?
Right. So there's nice physics, but there's also good motivation. And that motivation comes from particle physics. So we know that the standard model of particle physics is incomplete, because we've measured neutrino masses and there is dark matter, and dark matter doesn't fit into the standard model. Now, with accelerator experiments, you can't really probe things beyond the standard model at energy scales beyond the standard model very high. But with cosmology, you have the chance.
Yes.
So now I would divide particle physics models which go beyond the standard model. I would divide them into 4 categories. And let's make the analogy with different kinds of metals. So if you take a metal in the fluid state and you cool it, then certain metals will lead to defects, like crystal defects. Some metals will have no defects. Other metals will have point-like defects. Another class of metals will have line defects. And a fourth class will have planar defects. And it's similar in terms of in terms of particle physics models. Some particle physics models predict defects which are planar. Those are already rolled out by cosmology. Then others predict defects which are linear. And those have very interesting signatures in cosmology, and they are constrainable, and therefore they are fun to work on. And also interesting, because if you could find a signal of a cosmic string in the sky, you would have then shown that the way beyond the standard model of particle physics is in this one class of the 4. So bottom line is that there's good motivation to look for the signatures of cosmic strings in the sky. Now, cosmic strings produce signatures in the microwave sky. They produce lines in the sky across which the temperature jumps, and they produce rectangles in the sky where there is extra polarization with a uniform direction. and a linearly increasing magnitude. And that includes B-mode polarization.
Mm-hmm.
So you could go after this, and you could ask the question, if you have a map of polarization with a particular accuracy, how severely can you constrain particle physics models which have cosmic strings? There's one free variety in those models, and this is the tension of the strings. And the tension is already constrained because we haven't seen in temperature maps of the microwave background, we haven't seen these jumps. So there are things like that that you can, there's good motivation for looking at the microwave sky in polarization independent of inflation.
Mm-hmm. So, and there are, of course, many, many others. And I did not mean in any way to impugn the kind of deep passion that all of my colleagues find. As I said, the neutrino mass is amenable to cosmic microwave background polarization measurements. Let me ask you, parenthetically, Robert, if we measure with the Simons Observatory, or maybe with the dark energy surveys or baryon acoustic surveys, some combination of cosmological experiments, they measure for the very first time in human history the mass of an elementary particle, such as the neutrino. Will your fellow particle physics theorist, will they believe us?
Oh, can I pass on that? Because simply, this is a very good question. And you ask me to comment on what other people will say, and I simply don't. I don't have a good feeling. I don't know.
But I'm
make controversial comments about other things, but about this, I would like to pass.
Okay, good, very good. That's totally within your right. So when to be fair to my audience members who are the brightest in the known universe, they will say things like, well, what else gives us credence in string theory? I agree. I often joke, and it's hard to do this in front of you, but I often say, like quantum computers are very good at figuring out what quantum computers can do. As Feynman said, they'd be very good at calculating a Lagrangian. But I don't know about you, Robert, but when I'm trying to board an airplane, I don't need my iPhone to diagonalize a Hamiltonian. So that's not practical. Similarly, I feel like string theory and the mathematics associated with it is very, very advanced. It's very, very much in the spirit of being useful to string theory itself. And I wonder, to my audience members who are wanting me to ask you, well, what does string theory predict? What is the resolution of swampland? How do you reconcile this theory that past guest Eric Weinstein, as a very good friend of Stefan Alexander and mine, has said that it's really devastated the careers of numerous young people because it kind of was a cartel for a long time in his mind. But he's not here to defend himself or even advocate for what he believes. But there's sort of a program that came from Natty Seiberg and Ed Witten and others that established a paradigm for the field over the last 30 or 40 years. And it hasn't really borne fruit. And in fact, past guest Jim Gates, who's been on the podcast many times, similarly, supersymmetry. These are things that no longer, they were very promising because of the beauty, elegance, simplicity, but do they have to connect to empirical verification? What do you say to that?
Right. So here, I'll make a great defense for string theory. So first of all, I'm convinced that gravity has to be treated quantum mechanically. And you can do Duncan experiments. You can imagine little experiments where you can show that you get the wrong result if you try to treat gravity classically and you keep a matter description of a quantum description of matter. So maybe I don't have a slide illustrating that, but so now
can I just ask you, is that true also in black holes, because I've had this debate with Sir Roger, and I've said there's no there's no letter from God that says that we have this unification. First of all, we don't even have, if I'm wrong, correct me, but we don't even have a grand unified theory that's self-consistent. And I always joke we're putting the gut in front of the toe, or the toe in front of the gut. And we're now seeking a theory of everything, which would include quantum gravity and subsume it, but we don't even know how to unify the other forces. So it's like get the dust particle out of your eye. So anyway, how do you react to that? I mean, why do you say with confidence?
So I would argue that we need to quantize gravity. So now let me make another argument for that. Let's take a point particle. A point particle will have it has a particular mass, and it creates a gravitational field. Now you make the mass higher and higher, and eventually the extent of the particle becomes smaller than the Schwarzschild radius. And instead of having a particle, you have a black hole. So if you treat matter quantum mechanically, you have to treat gravity quantum mechanically. So that's the starting point. So now, I would love if there were different candidates to do this, but I view string theory as the most promising way to quantize matter and gravity in a unified way. Now, I said early on that we don't know how to do it in full generality. We don't have what I earlier called a non-perturbative string theory. But I think that there are two aspects of a theory that is needed if you want to describe the early universe, and also physics at very high energy scales. And this is we need both quantum gravity, and we need unification and a quantization of gravity. So again, I'm not a string theorist.
Yeah.
So I look around what is there in the market, and string theory is promising. One of the reasons why string theory is promising is that there are no singularities associated with those singularities of the same type that there are for point particles. If you scatter point particles and you do a calculation which is the next to simplest one, then you find that the probability that point particles scatter is infinity. And then you have to do something called renormalization.
That's right.
To get rid of this infinity. So now I was very fortunate to have taken quantum field theory from a very good lecturer, Sidney Coleman. But I was more fortunate that there was a famous mathematician, the differential geometer Raoul Bott, who was taking the class. Not just occasionally, he would come to every class, he would sit in the front row every time, take careful notes, and he would ask all the questions that we students were too embarrassed to ask. So this made the class really good. And there was one point where Raoul Bott became a little bit not so polite. And this is when Sidney Coleman introduced the concept of renormalization. And then he laughed out, "Is this what you physicists do?" And he continued taking notes. But it was absolutely clear to me that there was no way in which Raoul Bott accepted this renormalization. Now, this renormalization happens not to matter. If you do experiments at CERN, it works fine.
Right.
If gravity is involved, you simply cannot throw away these infinities. That's a cosmological constant problem.
And is this? I should point out that Raoul is credited as being the thesis advisor for Eric Weinstein, although Eric says he was not his Well, in practice, he was not his advisor, but I'll let Eric respond at some other point to that. But so yes, it is true. I mean, Feynman accepted renormalization, but he did in the electromagnetic context, but he did not accept it in a string theoretic concept. Of course, by the time he died, the cosmological constant problem really wasn't known in 1988 when he unfortunately passed away. But you did mention, this unification, and I guess, just again to push back with respect. So I did have on Shelley Glashow 2 or 3 years ago, and we talked about his SU5, and I always say that we're kind of led along the path that financial advisors tell us we should not. Oops, sorry, my computer assistant is now pinging me, but that's okay. Financial advisors will tell you that past performance is no guarantee of future results, and I think sometimes there is so much success in the realm of unification and symmetry and so forth that it became almost an expectation that the successor theory to provide quantum gravity would be in those same vein as Shelley tried to do after the success of the electroweak theory with Weinberg and why am I blanking on their third colleagues and Abdus Salam. So they were very successful, but not as successful looking at a concept like SU5. And I know this is not, again, it's not something you specialize in, but do you think we really need more of that kind of, the more research along this realm will provide and bear fruit? Or is it really going to take one of the young people that's, as you say, maybe listening to this in high school or in college, or freshman in college, some new ideas that we have become, kind of over beholden to what got us here, but it's not going to keep going along the path that we need to travel?
Yeah, so for me, string theory is a promising approach if we want to understand the very early universe, and if we want to develop a theory which is also true at the highest energies, smallest length scales. Now, do we have the tools right now to make detailed predictions, especially for particle physics? And there the answer is no. Mm-hmm. We need some new insights. And I think we might need a completely new approach to string theory, but I think this new approach will not go back to point particles. It will have something that looks like strings in it.
Is this related to the matrix theory cosmology?
Yeah, this is related.
Can you go ahead to slide 53, please? Or 52, please? And then share that. Yeah, continue to share that. So in matrix theory cosmology, again, I'm just a simple, humble experimentalist that you remember, breaking things on the roof of Barris and Holly. But the notion of emergence comes up a lot. What does it mean that time emerges in matrix theory cosmology? What is that? What does emergence even mean?
So for me, it's construction. It is, so maybe I should go back a little bit.
Okay.
And I know that Neil Truax, when he was on your show, he showed a technical slide. Mm-hmm. So I will now show a technical slide as well.
You get one per episode, Robert. One per episode. No, I'm just kidding. Right.
And so he showed his slide, and sort of was arguing that this was very elegant. But there were a lot of symbols here. Mm-hmm. So now what I'm showing you here, this quantity called L, this is the model. This is all that's contained in the model. And these X sub i's, these are these matrices. And here there's something that contains a time derivative. So here in this model, there is an initial time, mm-hmm. but we take this quantum mechanical model in a finite temperature state. So we then have to construct a new time. Okay, so out of these matrices, we have to build something that acts like time. That's what emergent means to me.
So it's mathematical. It's a kinematic emergent. It's not to be taken like, in other words, Hawking in his work would talk, and Hartle would talk about imaginary time, and then the imaginary time would sort of cleave off from being complex into being real.
That's right.
Is this a trick? But he called it a trick in the book. Yes. If you read it, is this a trick or is it real?
I think it's a trick.
Okay.
So if he called it a trick in the book, I agree with that statement.
Good. Very good.
So everything comes out of these matrices. Now, if you look at the details of these matrices, there's something hidden, and there's hidden in this D sub T, there's hidden the fact that there's another matrix. So there's actually 10 matrices, 10 dimensions of space-time.
Yes.
And time is associated with this matrix here. And let me digress a little bit technically. These are Hermitian matrices, so we can diagonalize one of them. We diagonalize the diagonal elements of time. So see, this matrix gives us time, and these xi matrices give us space in a way that we make precise.
Interesting. So your countryman, your country of origin is, of course, Switzerland. And this gentleman here attended an institution there called ETH. Yes. It's Albert Einstein. For those that are only listening, there are many, many listeners out there into the impossible landscape. And he was influenced by Lorentz and others, who Lorentz, I believe, said that, time and space are illusory and they're doomed, in a certain sense. And again, it's one of these kind of, slogans that I never really understood. And what does that mean, that space-time is doomed? Does it mean that, like, in the future we'll think, I can't even think about it, because we've always thought about, maybe in the past we thought, well, this magnet is different than an electric, field, but now, I don't think the average person thinks, oh, when I see a magnet, that's just a manifestation of U1 gauge symmetry, and it's actually the same thing as an electric. No, they think of it as a magnetic field deflects a compass and puts something on my refrigerator that my kid drew, and an electric field is, responsible for charging my Tesla. But what does it mean that heretofore space-time are doomed and so forth? What was Lorentz talking about, and why did Einstein, your country, what did he make of it?
Okay, so if you take flat space with no matter, then there's still space and time coordinates.
Yes.
But they don't mean anything physically, because there's nothing to measure anything. There's no matter to measure anything.
Right, it's empty, right?
Right. Now let's take cosmology. Let's take a universe which is the same everywhere, which is homogeneous and isotropic, but it is filled with the microwave background. So now you can measure the temperature of the microwave background, and we can use that as a clock.
Yes.
So Lorentz was not considering, he was considering empty space-time. So I think that as coordinates, the coordinates x and t, which physicists often use, they have no well-defined physical meaning. But as soon as you have matter in the system, then you can define physically well-defined clock variables. These are relational time. And so similarly, in this matrix model,
yes,
these are matrices. There's the part of the matrix which is homogeneous. There's a part which is fluctuating. So there is matter in plus emergent space and time. So the time coordinate can actually measure something. So this is emergent time with a physical meaning.
Very good. Well, you've done it again, because you're one of the best educators that I've ever met, Robert. And I often try to ape and mimic you, but I do a poor job. But one thing I'm curious about, when you teach cosmology now, this is an ethical dilemma that I struggle with. Do I teach them about positive curvature universes, negative curvature universes, when I know from my colleague, my late great mentor Andrew Lang, and of course my current friends, Lyman Page and others who are very much mentors to me, that the universe is flat and the spatial curvature is flat, and it's flat as far back as we can really constrain it. But it's so mathematically entertaining to talk about a positive space-time. And I remember you teaching it to me. The only cosmology class I ever took was by you. I audited it as a graduate student. I don't even think I finished it, but the point being, it had such an impact upon me. I remember you teaching us about it, but that was in 1996, 3 years before Boomerang, Maxima, and the Toko experiment. So, Robert, as a professional, dishing back and forth, do you teach your students about positive curvature universes, or do you just skip it altogether?
No, I do.
Okay.
Because observationally, we don't know that the universe is absolutely spatially flat. We just know that the spatial curvature is very, very small.
Yes.
In fact, the microwave experiments have given the bounds.
That's right.
So we don't know whether on scales much larger than the visible universe, whether space continues to be flat. Mm-hmm. So yes, I do teach.
Okay. Good.
I do include spatial curvature.
Okay.
In my discussion. So that part of my course has not changed.
Okay, very good. Was there more that you wanted to say about that? What is a 't Hooft limit? What does that refer to? I'm hoping to have Gerard on the podcast at some point. I've communicated him through Lenny Susskind once before, but tell me, what does that mean, the 't Hooft limit? At Hooft limit?
Right. So you see that in this model, in this capital L, there are two free parameters. There's this G, which is like a coupling constant, like the coupling constant which you have in electromagnetism. Right. And then there's a capital N, which is the size of the matrix. And so the 't Hooft limit simply means that you take this limit when n goes to infinity, adjusting this coupling such that the G squared times n remains fixed.
I see. Okay, very good. Was there more that you wanted to say about these slides before we come to the conclusions of both the episode and the presentation?
No, I think you should decide where you want the discussion to head.
Well, I guess I would like to talk about, to take a step back before we get any more deep into the weeds of cosmology, which I could talk about all day. And that's to talk about kind of the things that you're passionate about as a scientist and as an educator. Again, I think of you as an educator, both of my best friend, Stefan, and me personally, and many, many other students, and also bringing through Brown University many people who would go on to be my mentor, like Alexander Polnareff, who is a student of Yakov Zeldovich. And so it connected me to these greats of history. And I want to express my gratitude to you, but also to express that I utilize advice that you give. We have a lot of young people, mostly men, but I'm gratified to say there's a lot of young women. I'm hoping, your daughter will listen. My daughters will listen at some point to this podcast. They're very brilliant. But I have a lot of young people that listen, and some are academicians like us. I want to ask you, you once told me a very, very sage piece of advice. You said, before you move institutions, you said, Brian, you're going to move institutions many times. And you were right. You were 100% right. I went from Brown to Wisconsin to Stanford to Caltech. Ultimately, I went east to west, and then I went north to south, and now I'm in San Diego. I told my wife next stop is the Tijuana Institute of Technology, and so forth. And I've been to Antarctica multiple times. Yeah, so you're right. I'm going to move many times. And you said, at each place you go, write a paper and keep it in your drawer. This is back when we used to use drawers. And do you remember telling me this, Robert? And you said, yes, have that paper, because when you get to a new institution, you're going to want to have their masthead. You're going to want to have their, because they're now your boss, Brian, you said to me, and they're going to want something for their return on investment. And I thought, maybe that's true, but all that matters is me. It's just my career. So no, it's not true. It actually, the profession of being a professor, at least, hasn't changed. And it's very important to give attribution and to attribute to the place that you're at. I want to ask you, Robert, how has being a professor evolved since you started 30 years ago? And how would you do it again? Would you enter into this field again as a professor?
Right. So I think as a young person who's debating whether to start graduate school, then I would ask them, I would ask you, do you want to go for a career as a teacher or a career in business?
Mm-hmm.
A 9-to-5 job where you have to dress up in suit and tie, not just this jacket that I have, suit and tie, and or do you want a job where you can think about things, you can teach, you have a varying amount of teaching obligations, but you have quite a bit of independence and free time and security. Maybe you don't have the highest salary.
Right.
So this is a basic choice, and then you see that I don't give the student the possibility to say, I want to be a research professor at Caltech.
Mm-hmm.
That's completely unrealistic.
Right.
So if you say, I want to go the teaching track, then yes, you should study. First of all, you should study what you're interested in, but within the general area that you're interested in, you should study, you should pick a promising area. And for me, a promising area is an area in which there are deep questions and data. And there can be the balance between deep questions and data that can vary. And when I mean data, it's not data that's already there, but it's data that's going to come in. Now, when I started in cosmology, I mean, I got into cosmology by pure accident. There was essentially no data, and there were deep questions. And in the intervening time, there's been lots of data, but the deep questions have remained. So now what about the data? I see new observational windows popping up, for example, 21 centimeter cosmology.
Mm-hmm.
So right now, if a graduate student wants to work with me on cosmology, then I would say it is still promising because there are still the deep questions and there's still data. But I think this is a question that has to be revisited every decade.
Mm. And it does change. It does.
It changes. There are areas which have become, there are fields of physics which have become stale. The basic questions have been addressed, and there are lots of only details that have to be worked out.
One thing that's always typified you to me is your intellectual peripatetism, that you are not an experimentalist, but you are conversant with the potential of any given experiment. You are, as I say to my students, I kind of reverse what you would say to me. And I say, my experimental students, you don't have to do theory, but you have to know theory. In other words, you don't have to come up with an original theory or model like an experiment, like a theoretical graduate student might have to, or maybe not. Who knows what they do over there nowadays? But you should at least be conversant in it. What is the minimum that a theorist should know about experiment? A young person.
You know, this is a question that I should ask you. You should ask me the other question, namely, what amount of theory should a young experimentalist know?
Right. I guess I feel that I am going to be advising experimental students, and you're going to be advising theoretical students. So,
right. But what I try for back to your question, with my students, I try to have them follow what's happening in experimental cosmology. So we have a joint genre club between experimental and theoretical cosmology.
Mm-hmm.
So I don't know if I'm doing enough and if I'm doing the right thing, but this is what I'm trying to do. And you know that I tried to do that at Brown.
You did, yeah.
And I'm trying to do it at McGill as well. In fact, we have a very strong group here at McGill on the experimental cosmology side.
Very many of them are my colleagues on Simon's Observatory, Simon's Array, and other projects. So in that same vein, here at UC San Diego, I am the Associate Director of the Arthur C. Clarke Center for Human Imagination. And Sir Arthur C. Clarke had many, many aphorisms and quips. And I like to run them by you and get your response to them in sort of a final session before we wrap up when it gets too late, where it's getting very late and close to evening there. But I want to start with his first and maybe his best known aphorism, which is the following: any sufficiently advanced technology is indistinguishable from magic. I want to invert that and ask you the following question, Robert. If you're had to communicate to an alien civilization and they're going to come and devour the earth unless Robert Brandenberger tells them, no, don't do it, because we have created the following magic, what would that be? Would it be a technology? Would it be a theoretical discovery? Would it be something you did? What aspect of humanity is sort of the most impressive to you as an insider, but talking to an outsider?
Actually, physics is not the only thing. I think you asked some of your guests also about questions outside of physics. I would actually say that it is all of the art that we have produced.
Mm.
For example, classical music, which I really like.
Yes. And
it's all the literature. And I actually view science as in part art.
Mm-hmm.
So my pencil and paper scientific work, I think I'm obliged to sell it a bit as art, because our universities are publicly funded, and we need to give back something. So for me, it is very, very important to give back. But so I would include Einstein's equations into my list of cultural things that I would try to use to persuade the aliens not to destroy humanity.
I'm sure, and your capable voice and mind, it would be a slam dunk that they should keep us alive, at least for the entertainment. Another saying, and by the way, I do agree with you 100%, because my late great colleague here in San Diego, Hans Parr, who was a student of Leon Lederman's at Columbia, he used to say that relativity, GR, was the culmination of Western civilization. What are you talking about? Have you ever seen the Sistine Chapel, or have you ever heard a Bach fugue? He said, no, because to make relativity, it required the work of thousands of people in different cultures and different nationalities and different locations throughout space and time, language and deeply influential poetry and so forth. So I agree with you, and I agree with my late colleague Hans. I miss him tremendously, but it is overlooked because we often think that the main purpose of science is to produce technology. And I didn't hear any technology in your talk today, and I think that's perfectly acceptable, because that's what makes us uniquely human. You don't look at a baby and say, "Oh, what technology can it produce?" Okay, so I very, very much appreciated what you said, and I do believe it will work to prevent our devouring by aliens. Okay, next question it involves Arthur C. Clarke's famous movie, the 2001 A Space Odyssey. And there are these monoliths. I don't know if you've ever seen it, but there are these monoliths, these kind of, we don't know what they are. Could be a time capsule. It could be a warning. It could be something ominous. It could be something benign. We don't really know. But I like to think of it as sort of a last will and testament. And I want to ask you, in Judaism, we have a concept called the ethical will, a zava'ah. And the zava'ah is what you want to bequeath in terms of wisdom, maybe knowledge, but mostly wisdom and not monetary. So I want to ask you, if you were to write an ethical will for when you depart the mortal coil at age 120, please, no sooner, what would you put in an ethical will to give as wisdom to generations of not just your biological heirs, but your ideological heirs that I am lucky enough to consider myself a part of?
Okay, I will answer that question from the point of view of a teacher, in particular from the point of view of a student advisor. And the message would be that every person has their own strengths, and you should build on the strengths, and at the same time try to induce the person to work on their weaknesses.
Mm. Very good.
This is something that can be applied in all areas, I think.
And I think it's appropriate for you as a teacher, because, as I said, when you told me this thing, I remember it 30 years later. So it's obviously very meaningful to me about, kind of the obligations we have as employees to our employers and to the pursuit of science and a grand tradition. But I also have scaled that up, that I teach it to my students, who are like your grand students or your grand advisees in some sense. And so it scales. And your lessons live on, and they already are influencing people ideologically. So I thank you for that, Robert. Okay, we're almost done.
Another comment on that.
Yeah.
So maybe this is a message to the students who are listening. So this treating your fellow students, realizing that they all have their strengths. That's important also for students. While I was at Brown, I actually saw students discriminating against other students, just because they had different color of the skin and because they had a different scientific background.
Yeah.
And
I remember you were known for having students from as far away as Brazil and as close as New York and Trinidad, and it's quite remarkable. But it never it wasn't noteworthy to me. For some reason, I just thought that was natural of you, and that I didn't think, oh, Robert's going out of his way to mentor an African American or a Brazilian or someone from the former Soviet bloc countries. I just felt that's just Robert. But now I see
no,
it is.
Unfortunately, I've seen very different things happening.
Yeah. No, I think you're right. But let me ask you two more questions, if you'll pardon and have your patented forbearance and indulgence of me, Robert. And the first one is another quote by Sir Arthur. Well, I'll give you a bonus quote. So one of his favorite quotes of mine, at least of his that I like, is he says that for every expert, there's an equal and opposite expert. I won't ask you to comment on that, but I do use that on occasion when my department chair gets out of hand. But I will now pivot to two of his final comments. And the first one is this. When an elderly but distinguished scientist says something is possible, he is very much likely to be correct, or she. But when he or she says something is impossible, they're very likely to be wrong. First of all, do you agree with that? Second of all,
yes, I agree with that.
What have you changed your mind on? What have you been wrong about, Robert? If anything.
Okay, so in the 80s, I worked on cosmic strings as a competitor to inflation. And the boomerang data proved that this was wrong. So now, on a smaller scale, I often do make mistakes in calculations, and then I have to realize that there was a mistake. And usually, hopefully, you catch them when you repeat calculations many times. But there are some cases when you don't catch them, and then you have to live up to it and write an erratum. So there's one time when I wrote a paper with a friend of mine, and then we got a letter from a Stony Brook professor saying that no, we were wrong. And well, we argued for a while. We didn't just immediately believe it, but then eventually we agreed we had been wrong, and then we wrote an erratum. And then that Stony Brook professor wrote back and said, "I'm very happy that you wrote this erratum. Fortunately, I've never had to do that in my career."
Oh man!
What that Stony Brook professor had actually done, and then I realized why.
Well, I have a special bit of affection for
Stony. Can I also tell you something that my PhD, my de facto PhD advisor, Bill Press.
Yes.
What he told me, the advice that he gave me, he said that if you want to do something really new, you have to risk being wrong. And you see, when I'm working on this matrix cosmology, which I presented a little bit of, I may be wrong. There may be, since I'm not a string theorist, I'm going out on the limb. So, but it's exciting. And so you have to risk being wrong. And if I'm proven wrong, then I have to admit to it.
Sometimes when I am wearing my podcasting hat, I will say, in the name of one of my mentors in podcasting, James Altucher, he says, "I never publish something I'm not afraid to publish." I think that's an interesting rule. It doesn't mean that you should do stuff that's knowingly wrong or risky or unethical, but nevertheless, it's good to have that self-doubt, and but also simultaneously to have a little bit of swagger, to have confidence that you've been right in the past, and look back not on your to-do list, but on your have-done list. So the last question, Robert, brings us back to the very beginning, and this is going to be soliciting advice to your former self or a young person. As I said, a lot of young men, young women listen to this podcast. I want to ask you, in the name of Sir Arthur C. Clarke, he said the following. He said, "The only way to determine the limits of the possible is to go beyond them into the impossible." So I'd like to ask you, advice to your 20-year-old self. If I could have known you the same age that I started at Brown, what advice would you give that young Robert, or anybody as a stand-in for you, to give you the courage to do as you've done, to go into the impossible, the name of this podcast?
Pick a promising area to try to explore and explore it.
And not be led by other motivations, perhaps?
No. But you see, I gave this young Robert only two options. One option, a business career, and the other option, being a teacher, for example, at a community college, or in Quebec, Cégep, or in Switzerland, it would be gymnasium. I didn't give that person the option of wanting definitely a research professorship at a major university.
Because you didn't think it was possible? Or it was so out of the realm of possibility, or it was just too grandiose at the time? Why did you not give that young Robert that opportunity?
It's something that you can dream of, but you shouldn't consider that to be a probable possibility. I didn't.
Yeah, me neither. I didn't even believe it until maybe after I became a professor. And actually, I don't think, I mean, you touched on this briefly, but I'm worried about the future. Right now, we had a faculty search for a teaching faculty. We got 200 applications for one position. I joke that, there are more people playing in the professional NBA, or let me turn it to the Canadiens up there in Montreal. There's way more people that are, in the National Hockey League or in the Canadian Hockey League than our cosmology professors. And yet there's perhaps 5 times as many people who want to be that are in the minor leagues, if you will. And I'm not saying that pejoratively. I'm saying there are postdocs. Are there too many of them? Are there too many graduate students? I think overall, there's not enough. I think I would love to have 1 million cosmology students and postdocs and professors if it could be sustained, because I think that could lead to our flourishing as a species, and physicists in general, mathematicians, etc. But right now, I think we might have too many. What do you think?
I think we have too many people who are dreaming only of an academic career at a major research university. And you don't have enough who would be eager to go into a teaching career at a lower level position.
Well, I have to say, Robert, that you are in no small part to blame or to thank for setting me on a path as a paradigm. Again, I'd never thought, Stefan and I, we were in Barris and Holly room, 144 in the basement dungeon down there, we used to call it. And you'd come by every now and then, and you were inspiring to us. But we never thought we'd be professors. Him at an Ivy League school, me at a top research university as well. We never thought we'd be professors, but that didn't stop us from being fascinated by what you were teaching us inside and outside of the classroom. And so, on behalf of me and my students and my future students to come, I want to thank you so much, not just for being on the podcast. And I hope this will only be a part 1. And I hope part 2 will be in person at some point, because I miss you and I would love to be, to see you in person. But I hope this is just the beginning of our rekindling our connection. If you'll again indulge me with your patented forbearance.
Well, I'm very proud of what you've done. So it's always nice to see students succeed, and that's one of the pleasures of being a professor, to see students succeed and having fun and doing new things.
It is a great source of satisfaction. Robert Brandenberger, professor, longtime inspiration to many young generations of cosmologists and future and in the present. Robert, thank you so much for joining us. Enjoy your evening, and I do hope, as I say, we'll be in person not too long from now.
Thank you very much for the invitation.
Thank you.
Any sufficiently advanced technology is indistinguishable from magic.